Hello everyone, and welcome back. Today we're going to begin our journey and talk about sequences of real numbers, and there's plenty to talk about, so let's get right into it. So, what is a sequence? So a sequence is just going to be a function or a mapping whose domain is the set of natural numbers, usually starting at 1, but some people will start it off at 0 if they prefer to. And we say that that sequence converges to a limit L, and L has to be a real number, not an extended real number, at least typically. If and only if for any epsilon greater than 0, where epsilon is a real number, there exists another natural number n that depends on that epsilon, such that for all n in the domain of this particular sequence that is bigger than this particular n that depends on that distance, the distance between the sequence value and that conjecture limit is arbitrarily small, right? So as long as an gets arbitrarily close to L for arbitrarily large values of m, then we say that an converges to L, and some people will say that L is the limit of an, and we'll even write it as lim of an is equal to L. And in the case that a sequence does not converge, we will say that that sequence diverges, right? Some people will say converges to plus or minus infinity, but we won't get into that here, right? So let's look at a particular example of a sequence. So let us assume that let's call it am, is equal to k or m divided by n squared plus 1, where n is a natural number, right? So let's just look at a few terms of this particular sequence. So am, some people will write this sequence as n is equal to 1 to infinity, just to be clear about the domain. So it's going to be equal to what? So when n is equal to 1, we have 1 divided by 1 squared plus 1 that's going to be equal to 2. And then we're going to have 2 divided by 2 squared plus 1 that's going to be 5. And then we're going to have 3, 10, 4, 17, 5, 26, and so on. So the tops are just natural numbers, and the bottoms are just one more than the perfect squares of the positive integers. Okay, so what are the questions that we're interested in answering today? So the first question is, does this sequence converge? And if so, to what? And this is going to be a common question, actually, especially when we start getting into sequences of functions and infinite series later on, right? Usually answering the question, does this sequence converge, is usually a lot more easier to justify, prove, or disprove compared to, if the sequence actually does converge, what exactly does it converge to? Right? So if we actually look at a couple terms of the sequence and maybe generate a graph of this, so let this be n and let this be am, notice that when n is equal to 1, for example, we're equal to 1/2, right? And then when n is equal to 2, that's going to be 2 divided by 5, which is 0.4, right? So when we get to there, we're at 0.4. And when we go over here, notice that 5 divided by 26 in comparison to 5 over 25, well, which one of these is bigger? Because we know 5 divided by 25, that's just going to be 0.2. Well, if we make the denominator bigger, then the quotient becomes smaller, so that means that is definitely the case. So that means when n is equal to 5, we're somewhere slightly less than 0.2. So we do have some evidence to believe that this sequence is a decreasing sequence, right? And notice that regardless of the value of n, that's always going to be positive, that's always going to be positive. So we have a quotient of positive numbers that is in some sense always decreasing. So does this sequence approach some particular number? It could be a positive number, that much is possible. It could even be 0, but definitely can't be a negative number because the sequence will never generate negative values, right? So let's first off conjecture what the actual value of this sequence is. In particular, let's conjecture that the limit of this particular sequence is equal to 0. right? So it's always going to get closer and closer to 0. So how are we going to prove that the limit of this particular sequence is indeed equal to 0, right? So let's see if we can present a formal proof. So a couple notes before we get into this. So the first is that an is greater than 0, and that's true for all n in the set of real numbers, and you can probably prove that using mathematical induction quite easily. And another thing that you can prove via the properties of real numbers is that 1 divided by n squared plus 1 is less than 1 divided by n squared, and that's practically due to the fact that n squared plus 1 is greater than n squared. And that's going to imply that n divided by n squared plus 1 is less than 1 divided by n squared. N is a positive number, so I can multiply both sides of this inequality by m, and n divided by n squared will reduce to just 1 over n. So we have the comparison that n over n squared plus 1 is less than 1 over m, right? So we get that sequence of logic. So now let's jump into the formal presentation of the proof, right? So what we're going to do is we're going to choose an arbitrarily small but positive number epsilon, and we're going to see what we can get out of this sequence. So our claim is that an converges to 0. So 0 is the limit in this particular sequence. So that means the distance between our sequence an and L should be arbitrarily small if I choose my n large enough. Right? So what is an exactly? So an is n divided by n squared plus 1, and my limit claim is 0, right? So we clearly see that if we take a number and subtract 0, we're just going to get that number back again. So we have n divided by n squared plus 1, and we already know that this sequence is already positive, so the absolute value of a positive quantity is that quantity itself. So this is just going to be equal to n divided by n squared plus 1. And we already know that n over n squared plus 1 is going to be less than 1 over n, so we get this particular sequence. So now what do we need? So what we need now is we need to show that this distance is arbitrarily small, and 1 over n is not arbitrarily small, at least for a particular fixed value of m, right? So if n is greater than some natural number n subscript epsilon, then what will we have? Well, we know that if 1 over n, if n is the larger number of n and n subscript epsilon, that means 1 over n is going to be smaller than 1 divided by n subscript epsilon. And keep in mind what we want. We want this to be less than or equal to, either one is perfectly okay because we have strictly less than here. We want this to be less than epsilon, right? So somebody has chosen an epsilon, and you need to have or prove that there exists an n subscript epsilon, so this inequality is established, right? So somebody chooses an epsilon, you just need to find an n subscript epsilon such that this sequence of inequality is indeed the case, right? So all you need to do is you need to just choose n subscript epsilon to be bigger than or equal to the reciprocal of the epsilon that they have chosen. Because when you have done this, then what you have is, well, if n subscript epsilon is greater than or equal to the reciprocal of epsilon, that means 1 divided by n subscript epsilon will be less than or equal to epsilon, right? And if that is the case, well, what exactly do we have? So we can erase this conjecture thing, right? So we're going to choose, so you choose an epsilon, I choose my n, right? So if that is the case, 1 over n subscript epsilon will be less than or equal to epsilon. And if that is the case, then I have that this distance is arbitrarily small, right? So based upon that logic, then we have evidence, or we have proven, that the limit of n divided by n squared plus 1 is indeed equal to 0. Since we're working with introductory principles associated to sequences of real numbers, and we just gave you an example of how to prove the limit of a particular sequence, I actually want you to try this actual proof on your own because it's a little bit more easier than the previous one. And it's a very fundamental one in the sense that, you know, this function or this sequence 1 over n is actually very, very common, especially with comparisons. And it says that the limit of the sequence 1 over n is actually equal to 0. Right, so pause the video if you want to give this on your own, else let's see how to prove it. Right? So, as usual, we're going to start off by letting epsilon be an arbitrarily small but positive number. And obviously, if epsilon is greater than 0, then we know that 1 divided by epsilon is also going to be a positive number because the reciprocal of a positive is also positive as well. Right? So using some of the principles that we built before, in particular the Archimedean principle, we know that if epsilon is a real number that's positive and 1 over epsilon is a real number that's positive, that means there exists some natural number n such that 0 is less than 1 over n is less than epsilon, right? So for any real number, there always exists a positive real number in particular, there always exists a reciprocal of a natural that's in between 0 and that real number that you've chosen, right? Because epsilon is a real number, right? So if that is the case, so for n bigger than or equal to n, what do we have? We have that, well, if n is the larger of these two, then that means 1 over n is going to be smaller than or equal to 1 divided by capital M. And we already know that 1 over capital N is less than epsilon, so that gives us this particular distance. So going back to the definition of the limit of a sequence, what do we have? So the distance between 1 over n and the conjecture limit 0, we already know that that's going to be equal to the absolute value of 1 over n. N is positive, so the absolute value of 1 over n will also be positive. And we already have that 1 over n is strictly less than epsilon, right? So if that is the case, then we have proven. In some sense, we didn't really have to choose our n that depends on epsilon. We used a couple other theorems that we did before, in particular the Archimedean principle, in order to show that the limit of 1 over n is indeed equal to 0. The first theorem that I want to present today is actually quite intuitive if you've already taken calculus before, and it says the following. Suppose that you have a sequence that does converge, then its limit is unique, which means that if it does converge to something, it can't converge to something else simultaneously. Right? So how are we going to prove this? As usual with uniqueness proofs, usually contradiction is the way to go. So what we're going to do is we're going to assume that the limit of an is equal to L1, and we're going to show that the limit of an is equal to L2, and we're going to use the definitions of limits and convergence of sequences in order to justify that L1 and L2 are equal to one another regardless. Okay, so that means what? So that means for all epsilon greater than 0, then there exists, and we're going to do a two-part sequence of logic. In particular, there exists an M1 in the set of natural numbers and also an N2 in the set of natural numbers, such that the distance between an and L1 is less than epsilon, and an and L2 also less than epsilon. And that must be true for all n greater than or equal to n1 and n greater than or equal to n2, where n1 and n2 are those natural numbers that we chose, right? So notice in particular that if the absolute value of an minus L is less than epsilon, then that's also true that an minus L is also less than epsilon divided by 2, because epsilon divided by 2 will be smaller than that of epsilon. Right? So why do I even care about stating this trivial property? So since this set of L1 and L2, the set of proposed limits, is a subset of the natural numbers, that means, in particular, it's a finite subset of the minimal finite. So let's actually say that because that's important. So it's a finite subset of the set of natural numbers. That means a maximum of this set, L1, L2, exists. Right? Let's call it a number L. Okay? So this finite subset of the set of natural numbers has a maximal element. That's pretty easy to see using the theorems that we've already proven. So that means for all n greater than or equal to n, that means the absolute value of L1 minus L2, if L1 and L2 are different, then the distance between these two numbers cannot be arbitrarily small. So let's see what we get here. Hopefully a contradiction or something that leads into that realm. Right? So this is going to be equal to, since L1 and L2 are real numbers, we can add 0 to it. In particular, L1 minus an plus an minus L2. right? For some n where n is an arbitrary value, right? So by triangle inequality, since each of these numbers are real numbers, this is always going to be less than or equal to the absolute value. If we group those two and those two together, we're just going to have an minus L1 and then an minus L2. And here I've just reversed these two because the absolute value of minus 1 is just equal to 1. Right? So if that is the case, since an minus L1 is less than epsilon, it's also less than epsilon over 2. So that means that's less than epsilon over 2. That one's less than epsilon over 2. And the sum of epsilon over 2 and epsilon over 2 is just equal to 2 epsilons over 2's, which is just equal to epsilon. Right? So we have that the distance between L1 and L2 are arbitrarily small. That means that L1 minus L2 is equal to 0 by properties of absolute values, which means that L1 and L2 are going to be equal to each other, which implies that limits of convergent sequences are unique. The next definition is actually quite important, and it says the following. Suppose that we have a sequence an with domain, as usual, the set of natural numbers. Then we say the sequence is bounded if there exists a positive real number m such that the absolute value of the values of the sequence are always less than or equal to m for all n in the domain of that particular sequence. So let's sort of think about that for a moment of what we're getting at here, because if you sort of think about this, what we have here is that this covers both the sequence an being bounded above, and also below. Right? And you're like, well, how does that include both of them? So let's sort of draw a little sequence here. So let's assume that these dots represent the values of the sequences, right? So if this is a sequence, right? So let's assume that it is bounded. Then there exists some number, say m1 here. And there obviously exists some number m2 there. And if we assume that this distance here is smaller than this distance from 0 to m1, then when we take the absolute value of these negative numbers, we're also going to get numbers up here, right? So here is the absolute value of m2. Right? So if that is the case, if it is bounded, then it's also bounded above and below. Because if the values are between two real numbers a and b, then the absolute values are also going to be in between numbers 0 and m, where m is the maximum of the absolute values of a and b in that particular case. Okay, so let's look at a numerical example to sort of see if we can justify that a sequence is indeed bounded, right? So here we have an, and let's use the same sequence as we did before, n divided by n squared plus 1, right? So we know that n over n squared plus 1, we know that the absolute value of an, which is equal to the absolute value of n over n squared plus 1. We already know that since this number is always positive, then this is going to be precisely n divided by n squared plus 1. And we know that n over n squared plus 1 is less than n divided by n squared, and we know that n divided by n squared is the same as 1 over m. And we know that 1 over n is bigger than or equal to 1 for all n in the set of natural numbers, and you can justify that using mathematical induction as well. So we have that an's absolute value is less than or equal to 1 for all n in the set of natural numbers. That means an is bounded by 1, right? Or some people, in case an is not an always positive sequence, people say that the absolute value of an is bounded by 1, right? But by definition, we can say that an from a is equal to 1 to infinity is a bounded sequence. Okay? So, what is so useful about bounded sequence, and how does this relate to the convergence of sequences? So that's where the next theorem is going to come into play. It's going to try and connect these two. So if a sequence converges, then it must be bounded. So if a sequence converges, then that means there exists an m such that the absolute value of the sequence values is less than or equal to m. There must be. Now, a question, does bounded sequences imply convergent sequences? The answer to that is no, and you definitely should be able to provide a counterexample for that. But sequences that converge implies bounded sequences. That is indeed true. So if you want to try and prove this on your own, feel free to pause the video, else we'll get right into it. All right, so let's assume that this sequence converges, right? And if it converges, that means that the limit of this particular sequence, an, is equal to L for some real number L, right? So what does that mean in terms of definitions of sequence convergence? So that means for all epsilon greater than 0, there exists an n that depends on epsilon in the set of natural numbers such that for all n greater than n epsilon, the absolute value of am minus L will be less than epsilon. That's the definition of convergence, right? So now we're going to do some magic here. So we're going to let epsilon be equal to 1. Now this might not be obvious here, but we need to choose a particular epsilon in order to show that it is bounded eventually, right? So let's sort of see what we get out of here, but keep in mind, you can come back to this if you can't justify prematurely. Right? So if this is true, that means the absolute value of an minus L will be less than 1. And again, this is true for all n, or little n, bigger than n that depends on the epsilon I've chosen, which in this case is going to be called n1. Right? So what exactly is our goal here? So our goal is to show that the absolute value of an is less than or equal to m for some m in the set of real numbers. Okay, so let's start off by building the absolute value of am. So the absolute value of an is the same as the absolute value of am minus L plus L, because we already have some theory built on the distance between an and L, because that is a convergent sequence, right? So by triangle inequality, we know that this is less than or equal to the absolute value of am minus L plus the absolute value of L, because that's a real number and that's a real number too. Right? So we already know that by the choice of our epsilon, we know that this is less than 1. So that means this is less than 1 plus the absolute value of L. Okay? So what do we have here? So we have an is less than 1 plus the absolute value of L for all n in the set of natural numbers. So let's sort of write that down and see what we have here. So we have that the absolute value of a1 is less than 1 plus the absolute value of L. We have that the absolute value of a2 is also less than 1 plus the absolute value of L. And this is true all the way down, at least as far as we know, an1 minus 1, the term before that piece where it's not bigger than that epsilon chosen to be 1, right? And that's also going to be 1 plus the absolute value of L, okay? So what do we know about these absolute value of n's? Well, they're obviously all real numbers, right? So my question is, which is the larger absolute value of an? Well, it depends on the properties of this particular sequence. You can choose an increasing sequence, you can choose a decreasing sequence, you can choose one that adds slight sine and cosine, right? But nonetheless, it's the subset of the real numbers. So since it's a subset of R, it has a least upper bound, right? So what we're going to do is we're going to let m be equal to the supremum of the absolute value of a1, the absolute value of a2, all the way down to the absolute value of am1 minus 1. And also, let's throw 1 plus the absolute value of L, because it's possible that all of those are super, super small, right? So if that is the case, then since we have a subset of the real numbers, then by the completeness axiom, the supremum does exist, right? So if that is the case, then what we have here is that the absolute value of am is less than or equal to m. Right? So if that is the case, this m, since it always exists, that means that this sequence is always bounded, right? So that means am from n is equal to 1 to infinity is bounded, right? And again, that completes the proof. So if your sequence converges, that implies that it's bounded, and you should be able to provide a counterexample that if it's bounded, it doesn't necessarily imply that the sequence converges. The next theorem formally establishes some properties that you probably are already familiar with for limits of functions, and they are indeed also true for limits of sequences. So let's assume that an and bn are both convergent sequences with the limit of an being LA and the limit of bn being LB. Then, if we construct a new sequence from these sequences, For example, define Cn to be equal to the sum of the individual terms of the convergent sequences An and Bn, and then take the limit of that particular sequence. That sequence of summed values will also converge to the sum of the limits of the convergent sequences. Similarly, can be said for the differences between sequences converging to the difference in limits of the convergent sequences. Same thing can be said about the products and also scalar multiples of convergent sequences as well. Right? I'll prove 3, 1, 3, 3 for you, and I'll leave 3, 2, 3, 4 for you as well, since the proofs are very, very similar. Okay? So let's see if we can prove these very useful algebraic properties of limits. Okay? So if epsilon is greater than 0, so we're going to do it for both a, n, and bn simultaneously, then there exists an n1 in the set of natural numbers and also an n2 in the set of natural numbers, such that if n is bigger than or equal to n1 and n is bigger than or equal to n2, then an minus la will be less than epsilon, and an minus lb will also be less than epsilon. And we know that if it's less than epsilon, it's also going to be less than epsilon divided by 2. Okay, so since these numbers n1 and n2 are just natural numbers, what we're going to do is we're going to choose n to be equal to the supremum of n1 and n2. Because if that is true, then that means these two things are true simultaneously as well. All right, so if that is the case, what do we get as a result? So that means the absolute value of an plus bn, the sum of these sequences minus the claimed limit of the sum of those sequences, LA and LB, we need to show that this is arbitrarily small. So we already know that once we distribute that negative sign and then rearrange using the commutative and associative properties of real numbers, what we're going to have is that this is precisely the same as an minus LA, and then minus, actually plus, then bn minus lb. Right? And as usual, those two things are just real numbers for all n in the set of naturals. So the triangle inequality definitely is going to imply that this is less than or equal to an minus la and plus the absolute value of bn minus lb. Right? So as long as you choose n to be bigger than or equal to n, which is the supremum of n1 and n2, then this first is going to be less than epsilon over 2. Now, notice that this is true as long as you choose n to be bigger than n1. And this is true, the second one is true if you choose n to be bigger than n2. So if you choose n to be bigger than the supremum of n1 and n2, then both are true simultaneously. So that's why we need to choose that particular m, right? And epsilon over 2 plus epsilon over 2 is equal to epsilon, and epsilon is an arbitrarily small but positive number. So we see, equivalently, if we change notations, that's the absolute value of Cn minus the sum La and Lb is less than epsilon, which means that the limit of An plus Bn is actually equal to the sum of the limits An and Bn, which is equal to La plus Lb, as long as An and Bn are convergent sequences. That was the assumption. Okay. So let's see if we can also prove it for the product. The proof of the difference is actually almost the same exact thing, just a couple little minus signs shifted around. Okay. So what about the product? So if we look at the product, so A and Bn and the claimed conjectured limit LB, LA times LB, what does this converge to? So same thing with products, we need to introduce that, individual, we need to introduce somehow An minus LA and A or Bn minus LB. Right? We have to introduce these things because we know that this converges to 0 and this converges to 0 as well as n gets arbitrarily large, right? So the only way we can do it is to introduce some cross product terms so that we can factor. So the best way to do that, at least classically, is going to be letting this be equal to A and Bm and some cross product terms. And there's a couple ways to go about this, but I'm going to choose A and LB and then A and LB, the sum of and difference of those two. And then we're going to have our LA, LB term at the very end. Okay, so I'm going to treat those two terms as real number, those two terms as real number, and then triangle inequality this thing. So this is going to be less than or equal to AN BN minus AN LB, and then plus AN LB minus LA LB, and then we're going to start factoring out some terms, because notice that we have AN there in common, and we have LB there in common as well. And by properties of absolute values, this is precisely equal to the absolute value of AM times the absolute value of BN minus LB, and then plus the absolute value of LB times the absolute value of AN minus LA. Okay? So what exactly do we have here? So keep in mind, AN is a convergent sequence. So let's bring back a theorem that we proved a little bit ago, right? So AN converges, which means that AN is also bounded, right? So what we're going to do is we're going to let the absolute value of AM be less than or equal to M, where M is some real numbers. So M is your bound for that sequence. Okay? So also keep in mind that LB is also a real number. So what we're going to do is we're going to choose M, let's call it M star, to be equal to the supremum of M and the absolute value of LB, right? Which is obviously going to be strictly bigger than 0, because all bounds M must be greater than 0, and the absolute value is also greater than or equal to 0. So M being strictly greater than 0 is allowing us to say that this is strictly greater than 0. So if that is the case, so let's sort of go back to our sequence. So we have AN BN minus LA LB, right? So what do we have here? So we have that this is less than or equal to RM, and this is less than or equal to something, right? But nonetheless, it is a finite number. So if that is the case, then this must be less than or equal to M star times BN minus LB plus M star less than or equal absolute value of AM minus LB. Okay? So if that is the case, then what do we have? So now we're going to let, because we know something about these two things because they're convergent sequences. So what we're going to do is we're going to let AN minus LA be less than epsilon divided by 2M star. Because if the distance is less than epsilon, it's less than epsilon divided by some positive number, right? And it's positive because the supremum is strictly positive, right? So we're going to let AN minus LA be less than that positive number that's arbitrarily small because we control that epsilon. And we also have that BN minus LB also is going to be less than some arbitrarily small number. Let's choose it to be epsilon over 2M star as well. So if that is the case, then if we continue with this inequality, we have that this is strictly less than M star times epsilon all over 2M star, and then plus M star times epsilon all over 2M star. Those M stars cancel. We have an epsilon over 2 plus epsilon over 2, and we already know that that is precisely equal to epsilon. So we have that this is strictly less than epsilon. So that means that the limits of A and B and the product of these convergent sequences is indeed the product of the limits of those individual sequences, which is what we sought out to show. Okay? Now, I just want to ask this question, because this is also important, because we have that if the individual sequences converge, then there's some difference in product and scalar multiples also converge. But does the sum of sequences being convergent imply that both AN and BN, or we could say and or BN, converge, right? So I'll leave this question for you, but it's actually not a happy story. But keep in mind, if the sequences converge, I guess you could call linear combinations and products also converge. But if a function converges, it's possible that you can construct divergent sequences that add up into that convergent sequence. So that's a fun little thing to think about. now that we have some algebraic properties for sequence limits, let's see if we can find the limit of 2n plus 1 over n using those little properties. So in some sense, these properties allow us to avoid those epsilon and epsilon proofs, which is actually pretty convenient, especially if you don't like proofs. So since this is a fraction, we can decompose this fraction over addition since they are all real numbers. So we can write this as 2n divided by m plus 1 divided by m. And what is this? Well, this is just the limit of 2 plus 1 over n. So we've already shown that 1 over n is a convergent sequence, and the constant sequence converges to itself. So since these are convergent sequences, that means this is going to be equal to the limit of 2 plus the limit of 1 over n, and we know that the limit of 2 is 2 and the limit of 1 over n is 0, therefore this just comes out to 2. That means 2 is the limit of that original sequence. Okay, so these algebraic properties are definitely very, very useful. Now let's introduce a couple more theorems that you probably are intuitive to accept, but you can prove it using very basic proofs, using the tools that we've presented. So let's assume that an is a non-negative sequence, and let's assume that this is true for all n in the set of natural numbers. If this is true, then the limit of that sequence will also be greater than or equal to 0. Right? So if you have a non-negative sequence, then the limit will also be non-negative. Right? And I'll leave that proof for you because it's actually not too bad. And the next theorem that I want to introduce is the following. So if an and bn are convergent sequences, and let's assume that an is less than or equal to bn, and let's assume that this is also true for all n in the set of natural numbers. So you could in some sense say that bn is an upper bound for the sequence an. So it's a sequence could in some sense be an upper bound too. So if bn is always greater than or equal to the sequence an for all n in their domain, then what can you tell me about their limits? In particular, the limit of an will also be less than or equal to the limit of bn. Okay, so you in some sense have that if you can compare the sequences, you can compare their limits. And that can actually be very, very useful in several scenarios. So let's give this a proof because this is actually pretty fun. So what we're going to do, because if bn is always greater than or equal to an, then their difference, which I'm going to call bn minus an, this is always strictly greater than or equal to 0, right? So then we can use the theorem that I stated just before, right? So if that is the case, that means the limits, provided that an and bn are convergent sequences, which they are, then the limit of cn, which is going to be equal to the limit of bn minus the limit of an, because limits can distribute over differences of convergent sequences, that also will be greater than or equal to 0. So since those are just real numbers, we have that the limit of bn will be greater than or equal to the limit of an, which is practically the same thing that we sought out to prove. Okay? So that's a very useful theorem. Let's actually see if we can present a more useful version of this. So let's assume that the limit of an is equal to L, and let's assume that A is less than or equal to an. Actually, let's assume it's what's a good way to write this? Let's do L is less than or equal to an is less than or equal to u for all n in the set of natural numbers. And let's assume that L and u are fixed real numbers. This is not needed. You could actually make sequences out of the L and the u, so the sequences are both a lower and upper bound for the sequence an. But if this is true, then L will be less than or equal to the actual limits of the sequence L, and that's going to be less than or equal to, let's call it, say, u. Okay? And if you want to extend this, then this is going to be less than or equal to the limit of Lm, the limit of un, and so on. Some people will call that the squeeze theorem or the sandwich theorem for sequence limits, right? And the proof of that is actually not too bad, so I don't want to get into it here. right? So let's just do a nice little proof that you probably are familiar with, but I think it's a nice place to end for today, right? So we know that the sign of a real number, in particular a natural number, is always between -1 and 1. And let's assume that sign is already defined and it satisfies this property, right? So if this is the case, and let's assume that n is a positive natural number, then what you have is that -1 divided by a positive natural number will also be less than or equal to the sign of a natural divided by a positive natural. That's going to be less than or equal to 1 divided by a positive natural as well. Right? So if we have a lower bound and an upper bound for some particular sequence, we can take the limit of all three sides, and we can get some interesting results out of that. So what we have here by the theorem previously presented is that the limit of -1 over m will be less than or equal to the limit of the sine of n over m, and that's going to be less than or equal to the limit of 1 over m. And I know this is true because I know 1 over n and 1 over n are convergent sequences, and that -1 is just a scalar multiple of a convergent sequence. So the left-hand side is going to be obviously equal to 0. We've already proven that, or at least some variation of that, because we know that minus sign can factor out by the scalar multiple theorem for limits of sequences. So we have that that's going to be less than or equal to the limit of the sine of m over n. And that's going to be less than or equal to 0, and that one we have formally proven. And then there's only one real number that's strictly between 0 and 0, inclusive of those two boundaries. In particular, that must be 0. So we have that the limit of the sequence sine of n over n is precisely equal to 0. Right? So there's several other theorems and properties that are associated to sequences, but we'll get into them in the next video. I hope you enjoyed this one, and I'll see you then. Take care.